Yeah, there we go. Let me share my screen with you guys. Hello, everyone. Today today I'm going to do the last week of for the summer two semester. This is going to be like about a little bit over an hour because there's too many topics that I need to go over. Okay, so the topics are going to be sets, subsets, proper subsets, operation on sets, intersection of two sets, union of two sets, disjointed sets, Venn diagrams, introduction to probabilities, basic concepts of probability, multiplication principle, permutations, and combinations. So to begin, let's begin with the topic of sets. A set is a well-defined collection of objects. The first two slides have a lot of vocabulary and definitions because it's crucial for the students to know exactly what's going to be talked about. So for example, here is the first definition of a set. Examples of sets, well-defined collection of objects. So for example, example one, all the students in my math class. That's well-defined. That's a collection of objects that is well-defined. Example two, letters in the alphabet. That's also well-defined. Now let's do an example of a not well-defined set. So for example, the collection of young adults. That's not well-defined because what defines young adults? What's the age limit that's being considered to be young adults? So that's why this is not a well-defined set. How can we make it a well-defined set? Is maybe rearranging it. So for example, the collection of young adults between the ages of 18 to 29. Now that's well-defined, right? So this constitutes a set. Okay. Okay. Now to name sets, they use capital letters like such as A, B, and C are used to name sets. Each object in a set is called a member or an element of the set. The braces, the set braces or brackets, they are used to enclose objects in a set. Okay, so for example, this how you read this is set A, consists of the elements or members 3, 4, and 5. You see, set A consists of elements 3, 4, and 5. The symbol, this symbol here, like an E, is an element of the set, right? So this symbol here means it's an element. So, and the symbol, the symbol with a line across it, it means it's not an element of the set. Okay. So going back to the set A with elements 3, 4, and 5, so we can say that 3 is an element of set A, right? Because 3 belongs in A, or 3 is an element of the set 3, 4, 5, because 3 is inside the set. That's what the symbol means. And here you read it. 3 is an element of set A, or 3 is an element of the set containing 3, 4, and 5. That's what I just mentioned. Now, 2 is not an element of A. Why? Because 2 is not inside the set A, or the set 3, 4, 5. And here's how you read it. 2 is not an element of set A, or 2 is not an element of the set containing 3, 4, and 5. Sets definition and examples. Okay, empty set. Empty set means a set with no elements. And there's like, I believe, 2 different symbols for that. You see, there's my first symbol. The symbol like a null with a line across it, it means empty set, or the braces or the brackets with no elements in there, it also signifies an empty set. Equal sets. Equal sets contain exactly the same elements, exactly, they have to be the same, and the order does not matter. So for example, the set 3, 4, 5 is equal to the set 5, 4, 3, is equal to the set 4, 3, 5. So all these 3 means the same thing, right? They're all equal sets. Sometimes we describe a set by common property of its element rather than by a list of its element. What we've been doing up to this point, this is considered a list of sets. Now, the other option can be sometimes we describe a set by common properties of its elements. This property can be expressed with a set builder notation. So for example, this, the set X such that X has a property of P. Here's how you read it. The set of all elements X such that X has a property of P represents the set of all elements X having the same property as P. Okay, now let's break it down. The set means this whole thing with the brackets here, or the braces. That means the set of all elements X, right? Of all elements X, the little line like that means such that X has a property of P. Okay? That's how you read this, the set here. Okay, now, example, list the elements in the given set. The set X such that X is a natural number more than 5 and less than 8. A natural number are numbers that begin with 1 and they go all the way to infinity. So for example, a number more than 5 means 5 is not included, right? Because it says more than 5. So it's got to be 6, 7, and less than 8. So it's going to be 6 and 7. The set of elements X such that X is an integer and the integers are between -3, right? With the 3 not included because there's no bracket, I mean, like a line on the bottom, and the 1's included. So it's going to be -2, -1, 0, and 1. So this is the set that they're talking about, and this is a list of the elements. Okay, need to know whole numbers start with 0 and they go to infinity. Counted numbers or natural numbers, they start with 1 and they go to infinity. Okay, let me go back to the previous slide here real quick. Hey guys, all these right here are things that you have to know. Everything that can read, right? Like all the definitions and of sets, empty sets, and all that stuff, you have to know that. Okay. Okay, now these are the sets. State whether the statement is true or false. And I believe I got these from the actual homework from the book. This reads like this: 3 is an element of the set containing the elements 2, 5, 7, 9, and 10. Is this true and false? This is false because 3 is not inside the set. So that's false. 2 is an element of the set containing 2, 5, 7, 9, and 10. This actually is true because 2 is inside this set here. So that's true. Okay, that's how you read it, but this is true here. 2 is an element of the set. Number 3, 6 is not an element of the set 1, 3, 5, 7, 9. This is also true because 6 is not in the set. Okay. Number 4, 4 is not an element of the set 2, 4, 6, 8. This right here is false, right? Because 4, it is inside the set. So that's false. So 4 is an element of set. So the set containing 1, 2, 3, 4 is equal to the set containing 4, 2, 3, 1. This is true because all the elements of the set 1, 2, 3, 4 are also in the are the same elements in the set 4, 2, 3, 1. So that's true. Both sets are the same elements. The set ABC is equal to the set ABCD. This is false, right? Because these two sets do not have the same elements. For example, the first set, the ABC set, does not have the element D. Both sets do not have the same elements. The first set does not contain element D. Okay, now, number 7, all the whole numbers greater than 5 and less than 9. Remember, whole numbers start with 0 and they go to infinity. Okay, so all the whole numbers greater than 5, right? Greater than 5 is going to be 6, 7, and 8, right? And less than 9. So this is true. Right? Greater than 5 and less than 9 means whole numbers between 5 and 9. Number 8, all natural numbers not greater than 4. Okay? This is false because 0 is not a natural number. Okay? Yeah, or a counting number. Number 9, the set X such that X is an even integer between 5 and 19, right? And 5 and 19 are included. Let me see what even integer. So it's going to be 6, 8, 10, 12, 14, 16, right? This is false because we're missing the 18, right? That 18 is missing in the set. Number 10, the set with elements X such that X is a vowel equals to A, E, I, O, U. This is true because these are, all the vowels in the alphabet. Let me move on to the next slide. Okay, now comes two more definitions or concepts that we need to know. Subsets and proper subsets. And universal set. Universal set is a set that contains all the objects being discussed. When I teach this course, I actually tell the students that that my class, all the students in my class is considered to be the universal set because that's only my class, right? Nothing else can be in my class, only the students that are there. That's why we can say that my class is a universal set, or the set that contains all the objects being discussed. That's like an example of universal set. Subsets and proper subsets. A subset, here are the definitions from the book. A set A is a subset of set B. And this is how you write, this is the notation how you write it. Written as A is, this symbol here means subset. A is a subset of B, provided that every element of A is also an element of B. A set A is a proper subset of B, written in this form that A is a proper subset of B if element of A is an element of B, but B contains at least one element that's not a member of A. And lastly, when A contains an element that is not in B, then A is not a subset of B. We write as A is not a subset of B. What we have to know here, guys, is that this symbol here means subset, that every element in A is also in B, and this symbol here means that A is a proper subset of B, but B contains at least one element that's not in A. I believe that with examples, it'll make more sense. Now, but here are more definitions. For any set A, the empty set is always a proper subset of any set, or set A. And the empty set is also a subset of any set, and here the set A is being considered. And also a set is a subset of itself. Here, that's why here the A is a subset of A. Okay, now examples. We have set A, set B, and set C. Set A contains the elements A, B, C, and set B contains the elements A, B, C, D, and set C contains the elements C, A, B. Okay, now let's see what they give us here. Let me go back here. Here's how you read it, okay? Every element in A, right? This is true, right? Because every element in A is also in B. Right? Because here, right? Every element in A is also in B. So here, every element of A is an element of B, but B contains at least one element not in A. So this is also, that's how you read it. Now, for C, every element of B is not in A, right? So that's why this is not a proper subset, because every element of B is not in A, right? So you see every element in B, like the elements A, B, C, D are not in A because A does not contain the element of B. The D part here. Okay, let me go back here. A is a subset of C, right? Because every element in A, which is, every element in A is ABC, is also in C, which is CAB. So that's how you read this one. Every element of A is also in C. For E, A is not a proper subset of C. A is not a proper subset of C because A equals C, right? Because A and C, if you notice, set A and set C have the same elements. These are considered equal sets. And remember, for it to be a proper subset, every element in A must be in C, but C must contain an extra element that's not in A, right? And this is not the case. And F, the empty set is a proper subset of A, and that's true because the empty set is a subset and proper subset of any set. That was this definition here. Now here we go, okay? These are also from the homework. they say let A equal to the set of negative 4, 0, 4. B be the set of negative 3 all the way to 3, right, for the integers. And C is the elements negative 4, negative 1, 0, 4. D has the element of 0. E contains the element of negative 4. And the universal set is integers from negative 4 to 4. So here they want you to insert a proper subset or not a subset to make the given statements true. I believe they did a mistake in the book, but this is the way the instructions are in the book. But I believe this should have been also the line here on the bottom, like the book should be talking about subsets. But let's do how the book is, because this is actually some of the homework. Okay, so what goes here, guys, it's either a proper subset or not a subset. Okay, so for example, for A, negative 4, 0, 4, right, is a subset of the universal set, right? Because negative 4, 0, 4 are here on the universal set, on set U, which is negative 4, 0, and 4. So this symbol, the one is that goes there. Okay. For 12, E is negative 4, and A is negative 4, 0, 4. So also the same symbol is a proper subset. Okay, here's here I forgot to read how you read it. Every element of A is an element of U, but U contains at least one element, not in A. So for 12 will be the same element, the same symbol here, right? Because every element of E is an element of A, but A contains at least one element, not in E. Again, this is my set E, this is my set A. E, the negative 4 is an element of the set A, but A contains, right, two more elements that are not in E. That's why that's the symbol that goes there. If you reverse it, right, A is either a proper subset or not a subset of E. This will be not a subset. Okay. Every element of A is not in E. The elements 0, 4 are not found in E. For 14, we have B, which is negative 3 to 3, and we have C, negative 4, 1, 0, 4. So here, the same symbol, this symbol is going to go there because every element in B is not in C. It's not in C. Okay, and that's the reason behind it. Elements negative 3, negative 2, 1, 2, and 3 are not in C. The empty set, right? Remember that the empty set is a subset or proper subset of any set, so the symbol proper subset goes on the blank. The empty set is a subset and proper subset of any set. In 16, the set containing elements 0, 1, let me see D. So this will be not a subset. Why? Because D contains only 0 and 1 is not in D. Okay, 1 is not in D. If you reverse it, then this symbol, the proper subset symbol, goes here because D contains 0 and 0 is in the set 0, 1. Every element in D is an element of set 0, 1, but set 0, 1 contains at least one element that's not in E. Number 18, we have D and we have B. So this will be a proper subset, right? Because every element in D is also in B. But B contains more elements that are not in D. You see, every element of D is an element of B, but B contains at least one element not in D. Now let's see between A and C. This is A, negative 4, 0, 4, the elements. And set C contains negative 4, negative 1, 0, 4. So then every element in A is also in C. But C contains one extra element that's not in A. So this will be a proper subset. Okay. Hopefully this will give you enough information for you guys to know the difference between a subset, between a proper subset and not a subset. Now, here we're going to list all the possible subsets for each given set. Okay, for A part. Recall that set A is a subset of set B, then as A is a subset of B, provided that every element in A is also in B. So then, solution, right? So we have the 4 and 6. So to list all the possible subsets, we start with the empty set. The empty set is always a subset of any set. Okay. Then let's start with one element at a time. Then the 4 is also a subset of the set 4, 6. Also, the 6 is a subset of the set 4, 6. And now a subset is always, a set is always a subset of itself. So these are the ways it can be. 1, 2, 3, 4. So there's 4 subsets of any set with 2 elements. So a set with 2 elements has 4 subsets. Okay, now let's do B. So again, the empty set is always a subset of any set. Now let's go in the order. Let's do them one at a time. So the set containing A is also a subset of the set A, B, and C. The set containing B is a subset of the set A, B, and C. And the set C is also a subset of the set A, B, and C. Now let's do them in pairs. A and B is the set A and B is a subset of the set A, B, and C. The set AC is a subset of the set A, B, and C. And now comes the set BC is a subset of the set A, B, and C. And then finally, right, with 3 elements, a subset is a subset of itself. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So a set with 3 elements contains 8 subsets. So this leads to the next definition right here. A set of n distinct elements has 2 to the n subsets. So for example, going back to A, right? So A has two elements, right? So it's going to be 2 to the second power. That's why the answer was 4. If we do the one in B, right, with 3 elements, so it's going to be 2 to the third power. So it's going to have 8 subsets. So here, guys, I want you to find the number of subsets. So if you have only one element, it's going to be 2 to the first power equals to 2 subsets. If you have right here, you have 3 elements, right? Red, white, and blue are 3 elements. So it's going to be 3 elements, 2 to the third power equals 8 subsets. 2 to the third power is 8. X is a whole number less than 5. So here it's going to be 0, 1, 2, 3, and 4, right? It has 5 elements. 0, 1, 2, 3, and 4. So 5 elements will be 2 to the 5th power according to this to the rule here. 2 to the nth power subset, so it's going to be 32. Because 2 to the 5th power is 32. So also these are part of the homework, okay, from that section. I believe this is like self-explanatory. So let's move on to the next slide. Now comes operation on a set. Given set A and an universal set U, the set of elements of U that do not belong in A is called a complement. The complement of A is written like A complement, and you read it as, or you can read it as A prime or not A. I like to use the wording not A. So for example, the universal set of U would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And set A is 1, 2, 3, 4. Okay? So here's how you do it in a Venn diagram. This is U, right? And this is A. A contains, right? That's how you do it, right? So then this means the complement of A or not A, right? This is A. Everything not in the set is considered not A. Now let's do it with a Venn diagram. Okay, here we go, right? Let me go back here, previous and previous. So here we have find not A or the complement of A, right? Not A means not 1, not 2, not 3, and not 4. So what's left? 5, 6, 7, 8, 9, 10, 11, 12. So the complement of A or not A means the set containing 5, 6, 7, 8, 9, 10, 11, 12. Now let's do it in a Venn diagram. Okay. The set A, the set U or the universal set are all the elements from 1 through 12. So first, let's find set A, right? Set A was 1, 2, 3, and 4. So then not A means 5, 6, 7, 8, 9, 10, 11, 12 will be in the outside of the circle that represents A. So 5, 6, 7, 8, 9, 10, 11, and 12. Why are the numbers 5 through 12 not in the outside of the Venn diagram? Because the universal set, remember what it meant, that every element being considered. That's why this box here signifies the universal set. You see nothing outside, only this inside the box. That's why all the elements that are not in A, right, they go here inside the box, but not in the circle that represents set A. Okay, now given two sets, A and B, the set of elements belonging to both set A and B is called the intersection of two sets, and is written as A. The symbol here means intersects B, or elements belonging to both sets. I like to say this is the verbiage that I like to tell my students at times, because at times this doesn't make sense, all right? Because every student is different, so I like to say instead, what do they have in common means the same thing as elements belonging to both sets. So example, going back to the previous slide that we did, right? The universal set U was the numbers 1 through 12. Set A was the set containing 1, 2, 3, 4. And set B is equal to 2, 4, 6, 8. Okay, so let's find A intersects B. So what does A and B, what do they intersect, or what do they have in common? Right? They have in common a 2. They have in common a 4. So A intersects B will be the set containing the elements 2 and 4. That means intersection. What do they intersect, or what do they have in common? Now let's do it in a Venn diagram. This is set A. This is set B. Here's where they intersect. That's why A intersects B will be the portion where they intersect, or where they have in common. Now let's do it representing what we just did right here. So that's a universal set, right? This is my Venn diagram. So set A contains 1, 2, 3, 4, right? And set B contains 2, 4, 6, 8. Hey guys, when you do Venn diagrams, you always start where they intersect. If it's only 2 sets, so we start where they intersect. If it's 3 sets, you start where they all intersect. So here it's going to be 2 and 4, right? Because that's where they intersect. Then you're going to set A. Set A was 1, 2, 3, 4, right? So 1 and 3 has to be outside here. I mean, in the circle, but not here where they intersect. So here, set A, 1, 2, 3, 4. Then we go to set B. Set B was 2, 4, 6, 8, right? But 2 and 4 are already here, right? They're part of B, but they're also part of A. So what's missing is 6 and the 8. This is a representation of this problem here, okay, of A intersects B. Oh, hold on, I forgot something, guys. And then what's not in set A and set B, right, has to be here inside the box, but not in both sets. So what was missing? We have 1, 2, 3, 4, the 5. There's a 6, 7 is missing. 8, 9 is missing. The 10, the 11, and the 12. That's how you represent this Venn diagram here. Okay, now disjointed sets. Disjointed sets means that they don't have nothing in common, right? They don't intersect. That's what it means. They're both separate. So for example, again, the universal set with the same elements 1 through 12. Set A is 1, 2, 3, 4. Set B is 2, 4, 6, 8. And set C is 5, 7, 9, 11. So find A intersects C. If we notice, what do sets have in common? So if we notice, right, they don't have nothing in common. So these are called disjointed sets, right? Because they don't have nothing in common, so it's going to be the empty set, but they call it disjointed set. How do we represent this in a Venn diagram? This is my universal set. This is set A and set C. You see, there's nothing in common. That's why these are called disjointed sets. Now, That's universal set. Now let's do all let's do the Venn diagram describing the problem that we just did here, right? This is with a set. Now here with the actual elements. So set A contains 1, 2, 3, 4, right? Is in set A. And set C contains 5, 7, 9, 11. So what's missing, right? What's missing goes here inside the box, but outside of the two circles of set A and set C. So we got 1, 2, 3, 4, 5. What's missing? The 6. 7, we have the 8 missing. 9, the 10. The 11 is there, the 2 and the 12. That's the representation of this problem here, or the situation. Union of two sets or, right? The union means this stands for or union, same thing. Given two sets, A and B. The set of elements belonging to set A or B is called the union of two sets, and the written is A union B. Okay, let's do an example. I like to say list all the elements of both sets, but do not repeat them. Okay, here's the key word: do not repeat. You list them, you put them in the set, but you do not repeat them. Let me show an example here. Again, this is the same universal set, 1 through 12. Set A is the same as before. The elements 1, 2, 3, 4. And set B is 2, 4, 6, 8. Okay, so find A union B. The answer will be right. So we start with set A. Set A was 1, 2, 3, 4, right? Because this is first. That's why I put 1, 2, 3, 4. Then we go to set B. If the element of set B is already in here, we don't write it again. Is a 2 here already? Yes, a 2 is there. So we don't write it again. The 4 is a 4 here? Yes, it is, right? It's already there. How about the 6? The 6 is there? No, so we're going to put 6. Is the 8 inside here? No, so we're going to put the 8. So this is the A union B. Okay. Now let's do it in a Venn diagram. There's my universal set. This is set A. This is set B. So A union B will be all this right here. All this right here will be A union B. Everything here. Okay. Now let's do it with elements. There's my universal set. So first we start right. Set A. Set A had 1, 2, 3, 4. But remember, right? They had in common the 2 and the 4 going here. And then the 6 and the 8, they go here. And now whatever doesn't belong to both of them goes outside the circles, but inside the box. The 5, 7, the 9, the 10, 11, and 12. That's my representation, right? So it's all these right here, all these numbers. As I said, right, wasn't it 1, 2, 3, 4, 6, 8? You see, that's how you do that. Okay, now operation on sets. Let A and B be any set with U signifying the universal set. Then the complement of A is written as, right? That's a complement. It's also the complement of A means the set X elements such that X is not in A and X is not, and X is an element of U. That's how you represent this in set block notation. You see, that's what it means. The intersection, right? The intersection, this is the set block notation, but this is what it means, right? This is the intersection of A intersects B, means that's what they have in common. And for the union, right, A union B is a set elements X such that X is in A or X is in B or both. And that's the shaded part is how you represent that. Now these are the homework 23, 24, 25, 26, 27, 28 from that section. Okay. So here we start with the universal set is A, B, C, D, E, and 1, 2, 3, 4, 5. Set X is A, B, 1, 2, 3, right? And set Y is B, D, 1, 3, 5, and set Z is B, 2, 3. So since we're going to be needing the complement of both, I like to put all the sets here with its complement. So X is set X is A, B, 1, 2, 3. So then not X will be, right? So be not, if it's not A, not B, not 1, not 2, not 3. So what's left was C, D, E, and 4 and 5. So not X, or the complement of X, is a set C, D, E, 4, 5. Same thing, right, with a set Y. We go to the universal set, and it's not going to be B, nor D, nor 1, 3, 5. So it's going to be A, C, 2 and 4. A, C, E, 2 and 4. And Z is equal to B, 2, 3, right? So here, we don't need to find not Z, because not Z is not here, or the complement of Z is not here. That's not required on another formula. So let's start with 23. X intersection Y, or X and Y. So we're going to get an X, right? What do these two have in common? They have in common a B, they have in common a 1, and they have in common a 3. And that's it, right? So that's my X intersects Y. Now union, X union Y. So we start by putting everything in the set X, right? Because X was first. So it was AB, 1, 2, 3. Now we go to the set Y. If it's already in there, we don't write it twice, right? So let's do this. Is B already in there? Yes, so we don't put the B. How about D? Is D in here in X? No, so we're going to put the D. How about the 1? Is 1 already in there? Yes, it's there. The 3, yes, it's there. The 5, no, the 5 is not here, so we're going to put the 5, and that's it. So this is X union Y. Now, the complement of X, right? The complement of X. And here, guys, you put them in order, but if you put that on your MyMathLab or this, it doesn't matter. But most of the times when you check the solutions, they're going to give you the in alphabetical order and also in increasing order. So that's why this, but these two will be the same answer, right? If you put that on your MyMathLab, it'll be the same thing. So isn't it kind of correct? Now for 26. Where does the complement of X intersects the complement of Y? So we're going to go to, right, so these two here on top, right hand corner. What does the complement of X and the complement of Y have in common? They have in common C, they have in common an E, and a 4, right? And that's it. So that's my result. X complement intersects Y complement, or what does the X complement and not, what does the not X have in common with the not Y sets? So the same thing is C, the element CE4. Now, the not X, right? So the not X or complement of X is right here on the right side in red. So not X intersects Z. What does not X and Z have in common, right? Or where do they intersect? Do they both have a C in common? No. D? No. E? No. 4? No, not also, not 4 and 5, no. So it's going to be the empty set. Right? Is the empty set means the brackets with nothing, with no elements inside, or like the 0, or like the O with a slash across it, vertically. Now 28. X union Y intersects Z. So here we have to follow PEMDAS, right? So first we have to do the parentheses. What does X and Y, Y and Z intersect? So Y intersects Z, right? So let's go to Y and Z. They both have a common, right? They both have a B. So they both have a B. They both have a D, no, a 1, no, a 3. They both, it's going to be B3. So X union B with the say B3. So remember, if it's union, guys, or the OR statement, then we're going to put everything in X, right? So we're going to put everything in X. It's going to be A, B, 1, 2, 3. Then we go to the next set, right? To the one that is union with. The B is already there, and the 3 is already there. So that's my result, how it is. A, B, 1, 2, 3. Okay, now this is number 29, also from your homework. Okay, so here from the Venn diagram, they want you to list the universal set U, the set A, set B, set C, and where they both A and B intersect, where A and C intersect, and B and C intersect, and where they all three intersect. So you always start with where they all, right? So set U is going to be A, B, C, D, E, F, and G, right? That's my universal set. Set A contains A, D, G, E. Set B contains B, D, F, G. And set C contains C, E, F, G. Now comes A intersects B. What does A and B have in common, or where do they intersect? Right, this is A, and this is B. So don't they have D, G in common, right? Here's where they intersect. Now it's going to be A intersects C. So this is A again, that's A, and this is set C. So what does A intersect C? What do they have in common, or where do they intersect? Is right here, this area. So it's going to be E and G. Now comes B intersects C. So this is my B, and set B, and this is my set C. So they both intersect at FG, right? This is what they have in common, F and G. That's one result. Now, where they all three intersect will be this little portion here. That's where they all three have in common, or where they all three intersect. It'll just be the element of G. So this is my result for what they're asking for number 29. Now, number 30. Number 30, guys, here's where a lot of students have a little bit of confusion, okay? But I'm going to show you how to do a Venn diagram, okay? So here's what they have. Here's what they want. They want you to construct a Venn diagram, and then you have to answer the questions B, C, and D, which is how many people surveyed like comedies but neither dramas nor science fiction. How many people surveyed like dramas, science fiction, but not comedies? And finally, how many people like none of the movie styles? So you start with a Venn diagram. Hey guys, you always start, right? This is 60, right? Because they're saying that 60 people. So my universal set is 60. Only 60 people were contracted to respond to the survey. So let's call here, guys. Let's see, B comedies, right? Because they're talking about comedies, dramas, and science fiction. So let's see, B comedies. So that's my comedy set. And let D be dramas, right? So we can let either one of these two be D. So here I let that one be D. So this is my drama right here. That's it for dramas. So the one over here will be my science fiction. So I'm going to let S equal to science fiction. So that's going to be my S over here. Okay, now, hey guys, the main thing here, when we're going to be doing these type of problems, you always start where they all three intersect, right? So that's why I put this in red, because here's where they all intersect, right? 6 people like comedies, dramas, and science fiction. So this little portion here is where they all have in common, right? Where they all intersect. So this has to be 6 right there. Right, so we start there. So it's going to be right there. Then you can either start with intersection between two sets. It doesn't matter if it's C intersects D or C intersects S or any combination. Here, I'm going to follow the order here, right? 13 people like comedies and dramas. So comedies and dramas will be this portion here. But since we already have 6, right? And this is supposed to be 13, so 13 minus 6 will be 7. So the 7 goes there. Then it says 10 people like comedies and science fiction. So comedies and science fiction will be this portion here, right? So it's going to be 10, so we have 6, so the 4 is missing, because 10 minus 6 would be 4. Then 11 people like dramas and science fiction. So dramas and science fiction, so we're talking about this is a portion being considered here. Right, so it's 6, right? So 11 minus 6 will be 5, so that has to be 5. Then they're saying that 26 people like comedies. So 26 does not go here. It means the whole C is 26. So we have 4, 6, and 7, right? So it'll be 26 minus 17. which will be 9, right? Because 4 plus 6 is 10, 10 plus 9 is 19, 19 plus 7 is 26. Now let's go here, 21. 21 people like dramas, right? So all these here has to be 21. If we have, right, so we have, this is 11, this is 18. So 21 minus 18 is 3. So 3 goes here because this whole set D must be 21. Now let's go to science fiction, right? So science fiction is 25. So 4 plus 6 plus 5 plus whatever this is has to be 25. So we got 15. So 25 minus 15 will be 10. So then, right, the outside, right? The outside has to be, we're going to add all these up. And then we subtract that from 60, and that'll be how many people are on the outside, right? That they didn't like none of the movies. So we had 9 plus 7 plus 6 plus 4 plus 3 plus 5 plus 10, right? It's 44. So 60 minus 44 is 16. So 16 goes in the outside of all the sets, but inside the universal set. Now let's get to answer A, B, C, and D. So this is the answer for A, right? Let me go back here. Previous. So now the answer for A, right, is a Venn diagram now. How many people surveyed like comedies, but neither dramas nor science fiction? So here it means that we're going to go to the set of comedies, right, which is this portion here. How many people like comedies, right, but not dramas nor science fiction, right? So not these right here. Only, right, this is a set being considered, but only comedies, not these. So the answer is 9. Okay. How many people surveyed like dramas and science fiction, but not comedies, right? So we're going to go to dramas and science fiction. So dramas and science fiction will be this portion here, right? But not comedies. So the answer will just be, right, so it's going to be 3 plus 5 plus 18, right? Because it's saying how many people surveyed like dramas and science fiction, but not comedies. So we're going to go to dramas and science fiction, right? So these two here and these two here. So, but not comedies is going to be 3 plus 5 plus 15, right? Because they're saying dramas and science fiction, but not comedies, but not these right here. So it's going to be 5 plus 3 plus 10 is 18. Now for the last part, how many people like none of the movies, right? So none of the movies are the people that are down here. They're not included in none of the sets. So it's 16. So it's always wise to draw yourself like a Venn diagram. And actually it's easier because it's more visual. Now we're doing introduction to probability, guys. I know it's almost time, guys, but I believe I have like 4 or 5 more slides to go, guys, because this is actually really important here. So introduction to probabilities. Here we're talking about random experiment, a process by which we observe something uncertain. After the experiment, the results of the random experiment is known. The sample space is denoted by S, the set of all possible outcomes of a random experiment. Okay, so for example, for example, for the first example for a coin flipping space, the sample space, right? If we flip a coin, it's going to be heads or tails. So my sample space is H and T, right? H stands for heads and T stands for tails. We're rolling a fair die. Hey guys, a fair die means that, right, because it's like a cube, that every side is the same amount of weight. Because if it's not the same amount of weight, then the ones that weigh the more, the sides are an advantage for the die to land on those slots. So that's why, a fair die means everything is the same weight. So it can be a 1, 2, 3, 4, 5, 6, right? Now, but it's easier to draw a tree diagram to actually get the sample space. So for example, right, find the sample space of flipping a coin twice. So here's my first flip. It can be heads, right, or it can be tails. Now comes my second flip, right? So it can be heads the first time, right, with the first flip, then it can be heads, then it can be tails. Or it can be tails, right, on your first flip, and then after that it can be heads, or it can be tails. So what's my sample space? It's going to be heads, It can be heads, tails, or it can be tails, heads, and tails, tails. So my sample space will be the set HH stands for heads, heads, HT heads for heads, tails, TH for tails, heads, and TT for tails, tails. Okay, now, an event. An event is an outcome or a set of outcomes of a random experiment. An event is a subset of the sample space. For example, if the sample space for flipping a coin S is HT, then one event can be H or it can be T. Okay? Checkpoint. Suppose a die is tossed. Write the given events in set notation. The number showing is less than 3. So it's going to be the set, right? So this is my sample space. So it's going to be less than 3 will be 1 and 2. Number less than 3 will be 1 and 2. Okay. For B, the number showing is 5. So it's going to be just a set with the number 5 in there. See, the number showing is 8. That's going to be the empty set, right? Because it only goes from 1 through 6. So it's going to be the empty set. The die shows an even number, right? An even number will be 2, 4, and 6, right? The even numbers from the set. Okay, now here comes the basic probability principle. The set S, let S be a sample space of equal likely outcomes, and let event E be a subset of S. Then the probability that the event E occurs is the probability of the event to occur is a number from the event over the number of the sample space. Okay, let's do an example here. By the definition, the probability of an event is a number that indicates the relative likelihood of the event. Okay, the N of E is the number of elements in the event, right? The number of elements in the event. And N of S is the number of elements in the sample space. That's what I just mentioned earlier, right? So checkpoint. Suppose a single fair die is rolled with a sample space S is equal to 1, 2, 3, 4, 5, 6. Give the probability that each of the following events. So A, right? The event is the die shows an even number. So it's going to be, right, these are the even numbers. What was my sample space? My sample space will always be 6, right? So it's going to be 3 over 6, which is 1/2. For B, the die shows a number less than 10. So less than 10 is going to be all the numbers, right? It's going to be 1, 2, 3, 4, 5, 6. That's it, containing 1, 2, 3, 5, 6, which is 6 elements. What was my sample space? There's also 6 elements. So it's going to be 6 over 6 is equal to 1. For C, the die shows an 8. There's no element that shows an 8, right? So it's going to be 0 elements. So it's going to be 0 over 6, which would be 0. There's no way it can be an 8. Okay, now, checkpoint. A single playing card is drawn at random from an ordinary 52 card deck. Find the probability of the following. Of drawing a queen, a diamond, a red card, and a face card or an ace. Also, guys, when I actually teach this course again, right, when I teach it, I like to bring actual cards. That way, students can actually see what's taking place. But I believe with this PowerPoint, if I ever teach this class again with this PowerPoint, I'll be able to express it without bringing my deck of cards. Okay. So here's what it means. These are considered clubs, spades, hearts, and diamonds for the people that don't know about cards. There's 13 of each. 13 clubs, 13 spades, 13 hearts, and 13 diamonds. So there's 52 total cards, right? And also, I mean, I won't include the jokers, but the jokers will be 54 because it's always 2 jokers. But at times they don't. There's 52 total, right? Because there's from ace to a king, not including the jokers. Okay, now there's 26 blacks because 13 clubs and 13 spades will be 26, and there's 26 red between the hearts and the diamonds. Now, face cards. Face cards are the cards that actually have a face. That's why they're called face cards. So the only cards that have a face are the jack, the queen, and the king, right? That's why these are called face cards because they actually have a face. So there's 3 face cards for each suit. There's, for example, there's 3 clubs. There's a jack, queen, king of clubs, of spades, hearts, and diamonds. So now, to answer A, B, C, and D, what's the probability of a queen, right? So how many queens are there? There's going to be 4 queens because there's 1 queen on each suit. So there's 4 queens. So that's my sample space is 52, but there's 4 queens. So 4 over 52, right? You simplify, it'll be 1 over 4 over 52 will be 1 over 13. So that's your answer. Now for the probability of a diamond, right? How many diamonds are there? There's 13 diamonds. So 13 over the sample space, which is 52. 13 over 52 is about 1/4. The probability of a red card, right? So there's 26 red, right? So my sample space will be 26. I mean, my sample space will be 52, but red cards are going to be 26. So 26 over 52 is going to be 1/2. Okay. Now, the probability of a face card or an ace. So here, guys, how many face cards are there? There's 3 on each suit, right? So 3 times 4 is 12. How many aces are there? There's four aces, right? So 12 plus 4, right? This is for the face card. This is for the aces, will be 16. Over the sample space, which will be 52. Simplify it, so it will be 4 over 13. So that's my answer, 4 over 13. Okay, now let's do another example. Now we're doing 8.3, basic concepts of probabilities. Okay, now guys, the addition rule for probabilities. For any event E and F from a sample space S, the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersects F. Okay, this is example number 1, and I copied this example exactly from the book. Okay, so this is what they play in Vegas, right, or any casino. They play the American roulette. So let's read what it has. When playing American roulette, the copier or the attendant spins a marble that lands on one of the 38 slots in the revolving turntable. The slots are numbered 1 through 36, with 2 additional slots labeled 00 that are printed in green. Right here they are, the green, 00 and the 0. Half or the remaining slots are colored red and half are black. In a roulette, the slots labeled 00 are not considered as even or odd. So find the probability that the marble will land on red or even. How do we go by that? Okay, so let's do this. Actually, right, so it's saying about red or even. So let the set of red be R. So these are all the ones that are red, right? Because I went across the roulette the roulette table, and I counted all the red ones, right? So it's 1, 3, right, 34. They are right here, right in red. And then, right, so then let the set of even be E. So these are the ones that are even, right? For example, there's my 2. Where's the 2 at? The 2 is there's a 2, there's a 4, there's a 6, right? I have them all there. Those are the even numbers. So then we're going to apply the addition rule for probabilities. So it's going to be the probability of R union E, right? Union E is equal to the probability of R, which are red, plus the probability of even, right? Because the E stands for even, minus the probability of R intersects E. So then total of 38. So from the 38, 18 are red and 18 are black. Because remember, there's 38 and there's 2 green ones, right? So the 2 greens, they don't count here, right? As red or black. There's 18 even and 18 odd. So red and even, right? Because that's what you want. Red or even. So how many are red? So where do they intersect, right? So here where they intersect, red and even is going to be right. It's going to be here. These are red and even. So we got 1, 2, 3, 4, 5, 6, 7, 8. So red and even is going to be 8. So here we go. So how many are red? Right? Isn't it 18? 18 are red. How many are even? There's also 18, right? There's 18 even. And then minus, right? Where does the red and even intersect, right, the set R and E, right? So it's going to be 8, right? So it was this one here, red and even 1, 2, 3, 4, 5, 6, 7, 8. So minus 8 over 38. So it's going to give us 28. So the answer will be 28 over 38. Right? Simplify it. It's going to be 14 over 19. So that's my solution. And again, I got this example exactly from the book because I like this example because it makes the student think, right? They have to do a lot of work before they actually start. Start working. They have to get all the red ones right by numbers, all the even ones, and all that stuff. Okay, now example 2. Suppose 2 first dice are rolled. Find each of the given probabilities. The first die shows a 2, or the sum of the results is 6 or 7. Okay, so let's do this. So for part A, right, we have to use the addition principle. So we're going to let A represent the first event. The first die is 2, so A represents the first die is 2. And B represents the sum is 6 or 7. So here's all the possible combinations, guys, that when you toss or when you roll 2 for dice, right, these are combinations, right? So for the first one, it's going to be, right, the first die is a 2, right? So here you see the first die is a 2. So we got 1, 2, 3, 4, 5, and 6. So that's event A. And event B is the sum is 6 or 7, right? So if you come here across, right, so this is the sum of 6. The 5, 1, 4, 2, 3, 3, 2, 4, and 1, 5. And 7 will be 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. So all these have the sum of 6 or 7, right? So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the sample space, right, is 36 because 6 times 6 is 36. So for the event, right, for the first die to be a 2, right, it's going to be 6. And for set B, it's going to be 11. And where do they intersect, right? So we have to find A intersects B. So it's going to be 6 over 36 plus 11 over 36, right? Where they intersect is going to be 6 or 7. So it's going to be that one or that one. So it's going to be 2. So it's going to be minus 2 over 36. So my answer is 15 over 36. We simplify it. It's going to be 5 over 12. Okay. Now let's do the second part, part B. The sum is 11, or the second die shows a 5. So for part B, right, the sum, right, is 11. So again, the sample space is 36. So again, we use the addition principle. So we're going to let A be the sum is 11, right? And then and B be the second, right? So the 11 will be these two here, right? The sum is 11. And n of A is equal to 2, right? So n of A is 2 because it's only 2, that sum equals to 11. Now, for the second part, let B represent the event, the second die is a 5. So the second die is a 5, won't it be this one here? It's going to be this one here, right? Because you see the second die is a 5. So it's going to be all these right here. So it's 6, right? So then, where do they intersect? They intersect right there, and that's the only one, which is equal to 1. So now let's plug in all the values here. So it's going to be 2 over 36 plus 6 over 36 minus 1 over 36, which will give us, what, 7 over 36. So that's my result for part B. Okay. Now, this is called the complement rule. For any event E, the probability of the complement of E is equal to 1 minus the probability of E, and vice versa. The probability of E is equal to 1 minus the complement of the probability of the complement of E. Now, odds in favor of an event E are defined as a ratio of probability of E to probability of not E, or the probability of E over probability of not E. And not E, the probability of not E or complement of E cannot be 0 because it will be undefined. Okay. Observation. So the probability of E, right, is equal to n of E over n of S. And the probability of not E or the complement of E is a number of not E over the number of the sample space, right? So it's going to be right? So this will be my numerator. The number of elements on E over the number of non-elements on the sample space, right? When we divide, this becomes, right, multiplication, and these two we flip them, right? What happens with the elements of S on the sample space, right? They both cancel. So what's left? The probability of E, I mean the number of elements of E over the number of elements of not E. I like to use this observation here because all this means is that we're going to be applying this right here. Okay, so let's do an example. Right, from here we go here. So this is number 27 on page 434 on this from the book. A marble is drawn from a box containing 3 yellow, 4 white, 4 blue. Find the odds in favor and drawing the given marble. A yellow marble. Okay. So a yellow marble, by applying the concept here, right? So we have 3 yellow, 4 white, and 8 blue. So odds in favor of drawing a yellow, right? So it's going to be yellow. How many are yellow over not yellow? That's what that means here. How many are yellow? Is 3. Not yellow is 12, right? Because 4 are white and 8 are blue, so these are not yellow. So it'll be 3 over 12, which would be 1/4, but you have to write it 1 to 4. That's what that means. That's how you write the ratio of odds in favor. For B, odds in favor of drawing a blue, right? So it's going to be blue, but not blue. How many are blue? 8 over 7. So we write it as 8 to 7. A white marble. So it's going to be white over not white. White are 4 and not white are 11. So it's going to be 4 to 11. Actually, students like it when I explain it this way, right? Because it's much easier. Okay, and that's why I did the observation here, so you know that we can go from the probability of E to the probability of not E to the number of the event or the number of not in the event. Okay, we're almost done here, guys. I think I need like 2 or 3 more slides. So here, guys, this is actually exercise on 47 to 54 on page 435. Data from the 2016 General Social Survey can allow us to estimate how many hours people who classified their work status as part-time, full-time actually worked in the last week. Use the following table to find the probabilities of the events. Okay? So here we go. Solution. Right, so this is the probability of the event to take place. So we know that my sample space will always be 5091. That's my sample space. Now let's do number 47. Full-time worker, right? So full-time worker will be, right, we go here, full-time worker will be 1271. So it'll be 1271 over 5091. And we put in the calculator, guys. And most of the times I want you to round off to 4 places. So that's my answer will be 0.7989. Number 48, a part-time worker. So part-time worker, right? So part-time worker, we go here, is going to be 320. So it's going to be, the probability will be 320 over 1,591, which will give us something like 0.2011. Number 49, worked 50 hours or more, right? So this will be 50 hours or more, will be 393. So the probability for that to occur will be 393 over 1,591, which would be something like 0.2470. Work 0 to 19 hours, right? So we're talking about this one here. 0 to 19 hours will be 106. So it'll be 106 over 5091, which will be approximately 0.0666. Now, 51 through 54 are a little bit more challenging, okay? So those I'm going to do on the next page. I'm going to do one of each. I mean, I'm probably going to do what number, again, same concept. So I believe I'm going to do number, which one is he? Number 51 and I believe 53. So 51, part-time worker and someone who worked 40 hours. So here the key word is going to be and. So first of all, we go to part-time worker, right? So part-time worker is going to be 320, right? So it's going to be 320, but and right for the intersect will be part-time worker and someone who worked 40 hours or more. So it's going to be these two here, right? Because it's from here, from the 320 but only part-time worker, and they work 40 hours or more, which would be these two only. And that's where the N comes in, right? What they have in common would be this dots here. So it'll be 320, right? But that'll be the part-time worker, but since it's N, it's going to be what they have in common, so it's going to be these two here. It's going to be part-time worker and these two here. So my answer will be 70 over 5091 will be approximately 0.0440. Now look at number 54. A part-time worker or someone who worked for 20 hours or less. The keyword is or. So here, guys, we're going to go again to part-time worker, right? So part-time worker or work 20 hours or less. So this is a little bit more challenging to work out, guys, but by applying this principle, we'll be able to get it. Or we can do it, right? This can be actually seen with the table here. It's going to be 320, right? Part-time worker or 40 hours or 20 hours or less. It's going to be 320 plus 29 plus 42. Okay. Which will be, right? We can do it that way, right? So we have 320 plus 49 and 42 is going to give us the answer. But doing it this way will be 320, right? Plus 106, right? Because it says or 106 and 129 minus 77 over 87, which would be the same thing as what I said right now. It's going to be 320 plus 29 plus 42, okay? So we let A represent part-time workers and let B represent 20 hours or less. So for part-time workers, it's going to be 320. For 20 hours or less will be 106 and 129, right? But minus, because these two, we don't count them again, right? Because they already counted here with the 320. So that's why it's going to be 391, right? And if we add 320 plus 42 plus 29 will give us the same result, 391. Okay? So again, we simplify it. So it's going to be 0.2458. That'll be my answer. And again, the way I did it at the beginning was like this, guys, right? It says part-time workers, so we're going to go here to 320, right? Since it's or, we're going to add them all up, but we don't repeat them, right? So if these two here are already counted here, then we don't count them here on the 20 hours or less. So it's going to be 320 plus 29 plus 42. That's more visual. But this, how I did it, was actually by doing the work, by applying the adding principle. Okay, now multiplication principle, permutation and combinations. So this is called the multiplication principle. Suppose n choices must be made with m1 ways to make choice one. I think this was misspelled, guys, but I just copied and pasted. So this is misspelled here, I believe. So then there are m1 times m2 times blank times mn choices. Okay. So this is from page number 24 from page 477. It says how many different heating cooling units are possible if a homeowner has 3 choices for the efficiency rate of the furnace, 3 options for the fan, and 6 options for the air condenser, right? So by applying this principle, it's going to be right. How many are number of choices for efficiency rating? So it's going to be 3 for the fan speed, 3 number of choices for the air condensers, 6. So 3 times 3 times 6 will give us 54. So that's my answer. Okay, 54 different units are possible. Number 28 from page 477. The United States Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are not restrictions on the digits used? How many would be possible if the first number could not be a 0? So, right. So here we have to make the digits 0 to 9 make all the numbers. So these are all the digits possible. So 5-digit zip codes we're going to put, right? 1, 2, 3, 4, 5. So each one of these contains a digit from 0 to 9. For the first part, with no restrictions, means any digit from here can go here. So it can be 10, 10, 10, 10, and 10, right? Because any digit can go here with no restriction. So we multiply 10 times 10 times 10 times 10 times 10 will give us about 100,000. So that's the answer for the first part. Now for the second part, right? Now you have a restriction. The first digit cannot be 0. So this number cannot be a 0. So this number cannot be a 0, right? How many are left? So it's going to be 1 through 9. So this will be 9, and then 10, 10, 10, and 10. So it'll be 90,000. Okay? This is number 30. For many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. So no 26 letters on the alphabet and 10 digits make all the numbers. How many different license plates are possible with this arrangement? So they start with 3 letters. These are my letters. These are my digits. So it'll be 26 times 26 times 26, and then digits will be 10 times 10 times 10. When you multiply them out, you get 17,576,000. That's how many plates were possible. Now, for part B, when the states ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. How many new license plate numbers were then possible? So they reversed the order. So these are the digits and these are the letters. So same thing. 10, 10, and 10, 26, 26, and 26, right? So you multiply them out and you get the same answer as part A, 17,576,000. Now for part C. Several years ago, the number described in part B were also used up. The state then issued plates with 1 letter followed by 3 digits and 3 letters. So in other words, they only added 1 letter at the beginning. There's my letter, followed by the digits, and followed by 3 letters. So it's going to be 26, 10, 10, 10, 26, 26, 26. And if you multiply them out, we're going to get 456,976,000 possible combinations. Now comes factorial, n factorial. N factorial means for any natural number n. N factorial means that you're going to be multiplying, right? But it's going to be n, then n minus 1, then n minus 2 until you get to 1. And by definition, 0 factorial is equal to 1. Okay, so checkpoint. Evaluate 4 factorial. So 4 factorial will be the same thing as 4 times 3 times 2 times 1. That's what this definition means here. You multiply them out, it will be 24. 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. If you multiply those numbers out, it will give you 720. C, 1 factorial will just be 1. Now D, 6 factorial divided by 4 factorial. 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial will be 4 times 3 times 2 times 1, right? So the ones, right, that's 1 divided by 1 is 1. That also cancels as 1. And that's 1. And that's 1. So on the bottom we have 1, right? So the answer will be 6 times 5 divided by 1, which will be 30. Now comes permutations. Permutations, a permutation of a set of elements is an ordering of elements. For instance, there are 6 permutations ordering the letters A, B, and C. So these are all the possible combinations that you can put A, B, and C, right? So it's going to be 6. The order matters. For example, A, B, C, and C, B, A are 2 different orders, right? That's why here we have all the letters and different orders, and they all matter, so that's why there's 6. Example 3, how many batting orders are possible for a 9-person baseball team, right? So there are 9 possible choices for the first batter, and then 8, then 7, and so forth. So this will be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or 9 factorial, which would be 362,880. The number of permutations of n elements is n factorial. Okay, that's what this comes from. Now comes, right, or 9 factorial, right? You can actually plug this in the calculator, 9 factorial, and it'll give you the answer. Now comes permutations. If n PR, where R and n, where R is less than n, less than or equal to n, is the number of permutations of n elements taking R at a time. So this is my formula here. N elements taken r at a times, right, of a permutation will be n factorial divided by n minus r factorial. The order matters here, guys. So for example, say I have three letters A, B, and C. I would like to know how many two-letter arrangements are possible, right, where the order matters. So I like to use this example, right, so you guys can see the difference between permutation and combination, because combinations are next. So we have the letters A, B, and C. You want to arrange them and choose. So it can be AB or BA, right? Or AC and CA, or BC and CB. So there's 6 possible arrangements. If we're using the formula here, guys, it's going to be what 3 permutation 2, which would be 3 factorial over 3 minus 2 factorial, which would be 3 factorial over 1 factorial. It's going to be 3 times 2 times 1 divided by 1. The answer is 6. Okay. Or you have 3 letters and want to arrange them in 2, guys. You're going to put 2 blanks, right? How many can go here? 3. And then if one's already chosen, then 2 are left. So 3 times 2 is equal to 6. Or you can do it this way. Okay. This is number 40. This is number 40 from the homework, page 478. From a cooler with 8 cans of different kinds of soda, 3 are selected for 3 people. In how many ways can this be done? So by using the formula, so it's going to be 8 permutation 3. It's going to be 8 factorial over 5 factorial. Is going to give us 8 times 5 times 6 times 5 factorial. The 5 factorials cancel, right? So we're left with 8 times 7 times 6 will be 336. Or, right, you have 8 cans, you want to put them in 3, right? So you're going to put 3 blanks. 1, 2, 3. How many kinds of soda can go here, right? 8. Then once you choose one, right, you cannot repeat it again. So that's why it's going to be times 7, then times 6. Right? We get the same answer as using the formula. You see, you can do it either or. Now comes combination. In combination, the order does matter. Again, having the same letters as before, A, B, and C, we would like to group them in pairs. So AB is the same thing as BA, right? So AB and BA are the same thing. So it's going to be AB, AC, and BC. So it's going to be 3 possible groups. Using the formula, it's going to be 3 combination 2. Right, so it's going to be 3 factorial over 2 factorial over 3 minus 2 factorial. It's going to be 3 factorial over 2 factorial times 1 factorial. The 2's cancel, the 1 cancels, so it's going to be 3 over 1. So the answer is 3, right? So same thing. But I like to use only with 3 letters, or take it 2 at a time, because this actually you can see it. If there was like 4, right, like 4 different, like say A, B, C, and D, then this would be much bigger. That's why it's good to use the formula. But this I was trying to show you, like, so you guys can picture it in your head. Okay. Number 46 from page 478. 4 items are to be randomly selected from the first 25 items in a assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? So we have 25, right? 25 and 4. So it's going to be 25 combination 4, right? So my answer will be 4 times 3 times 2 times 1 is 24. So we're left with 25 times 23 times 22. It will give us 12,650. Or you can actually put that in the calculator, just the way it is. 25 combination 4. And enter it, and you'll get the result. Okay. Okay, now I believe I have 2 more slides, guys. This is permutation, guys. So these are the clue words for permutations: arrangement, schedule, order matters. And for combination will be group, committee set, sample, order does not matter. Okay. Okay, now number 59 from page 478. A lottery game requires that you pick 6 different. I forgot to put here the word numbers. 6 different numbers from 1 through 99. If you pick all 6 winning numbers, you win $4 million. How many ways are there to choose 6 numbers if the order does not matter? So for part A will be combination, right? Because the order does not matter. Combination. So it's going to be 99 combination 6. Okay. So again, I don't want to do all that work, but if you plug in the calculator, guys, will actually do the work. It's going to be 1,120,529,256. Now for part B, how many ways are there to choose 6 numbers if the order matters? So that's going to be a permutation. The number will be much more. Right? We use the permutations. This one will be 806,781,064,320. Okay, so again, by knowing the 2 words, you'll be able to distinguish if you use permutation or combination. This is number 60 from page 479. In exercise 59, you pick 5 out of 6 numbers correctly. You win $5,000. And how many ways can you pick exactly 5 out of 6 winning numbers without regards to order? Okay, so there's going to be a combination, right? Regards to order, combination. Okay, now, so this means here, guys, right? We're still playing the lottery. You have to pick 6 numbers, but if you get 5 out of the 6 numbers right, you win 5,000. So this is going to be a little bit more challenging. Okay, so first, 5 out of the 6 winning numbers right, because you want to get the at least 5 out of the 6 numbers right. So it's going to be 6 from the 6 numbers right. You want to get 5 right. So it's going to be 6 combination 5. Now remember, lottery requirements need to pick 6 numbers, right? So then from the right, if we take away 6, right? How many are left? From the 99, wouldn't it be 93? So 1 out of 93 losing numbers, right? Because remember, we have to get 6 winning numbers from 99. So we're going to multiply it. It's going to be 93 combination 1. These 2 in the front, right? These 2 first, that'll be like my n, right? They have to equal to 99, right? And then the r, right, which is n combination r, the second one must equal to the 6. That's where the 6 comes from. So 6 combination 5. Well, 6 combination 5 will be 6, and 93 combination 1 will be 93, so multiply them out. So that's your answer, guys, 558 possible ways. Okay, now this is the last one here. A financial advisor offers 6 mutual funds in high risk category, 7 in the moderate risk category, and 10 in the low risk category. An investor decides to invest in 3 high risk funds, 4 moderate risk funds, 3 low risk funds. How many ways can the investor do this? Okay, so the solution. If you read the problem carefully, the order does not matter. So here we go. From the 8 mutual funds, right, you want to pick 3. That's going to be 8 combination 3. From the moderate risk, right, you're going to choose 4. So it's going to be 7 combination 4. And from the 10 low risk, you're going to choose 3. So it's going to be 10 combination 3. Right? Then we're going to multiply them out. So 8 combination 3 will be 56. 7 combination 4 will be 35. And 10 combination 3 will give us 120. You multiply them out, and you get 235,200. Okay? So I believe that's it with this PowerPoint, guys. And I want to thank you for being patient. I went over by 30 minutes. I apologize. But I felt that it was crucial to explain everything that was here. Okay.
Thank you, Mr. Azasi. Thank you, everyone, for coming. I hope this helps on your final exams. Thank you so much for presenting. I'm going to go ahead and turn off the recording, but we hope to see y'all in the fall semester of 2021.